110. I'm going to start talking about sorting. Okay. Okay, announcements.
Okay. How's everyone doing? The midterm was like a week ago. Are you still booing me? Anyway, what's going on with the class?
Project 2B is due. I don't have the website up, though.
Yeah, get out the website.
We're late.
It's fine. Yeah, seems like Project 2B and 2C were due Monday, so if you're on extensions, I guess it's coming up now. Other than that, Project 3 is getting started. It's a great project to work on. One last thing, we do have our second software engineering lecture running this Friday. I'm unfortunately not going to be here. I'm flying out to St. Louis for the eclipse. Fun. Yeah, Perrin's going to be around to monitor the situation. We'll have our guest lecturers come up and talk a bit more about how Project 3 works and how you can work in a team most effectively.
Sounds good. For people on recording, we do that every day, but this is the first time you've seen it on tape. Okay. Let's talk about more sorting. So you've seen two sort algorithms so far, selection sort and heap sort. And today I will show you 2 and maybe 3, if time permits, sorts. So I hope everyone's ready. Okay. So before I talk about merge sort, I will quickly show you selection sort. And remember, selection sort, the way it worked was I had an array, and I repeatedly find the smallest item, swapped it to the front, and when I swapped it to the front, I knew that was its true place, and I could fix it, and I never had to move it again, and then I could sort the remaining unfixed items. And we also saw that this is n-squared runtime, because, well, at the first step, I have to scan n things to find the smallest item, then I have to scan n-1 things to find the smallest item, then I have to scan n over 2 things, and if I add that all up, well, that ends up being an n-squared sum, or theta of n squared. Okay, so here I'm going to introduce something that's a little bit maybe vague, but hopefully helps us with our intuition. So if I say that this runtime is theta of n squared, then I could roughly say, it's not an exact count, but I could maybe roughly say that if I had an input size of size 64, well, then I could say the rough runtime is 4,096 arbitrary units of time. And that number is 64 squared. So it's kind of a guess, but if I'm saying that the algorithm is n squared, then I could maybe say if the size of the input is 64, then my runtime is approximately 64 squared. It's not perfect, but it's good enough for the analysis that we're about to do. Okay. Good. So that's the first prelude to merge sort. We remember selection sort. We remember its runtime. And we also found out that if you want to, you can kind of approximate how long it takes by substituting in specific numbers. And that's just for the purpose of seeing the analysis. That's not an exact count or anything. OK. The second thing you have to see before I can fully present merge sort is an operation called merging. So the operation merging is as follows. Let's say I give you 2 sorted arrays. They're completely separate, and each one is sorted. And I want you to combine them into one really big sorted array. So the question for you is, how do I take those 2 arrays and merge them together into a really big array, knowing that both of the 2 input arrays are sorted? Also, how do I get that stupid zoom box to go away? OK, well, we're working on it. OK. So I guess let's go find a demo for merging. Oh, I forgot I linked to an external demo. OK, well, here's the demo for merging. So I have 2 arrays. Both of them are sorted. And my goal is to create one large array containing all the same elements that's also sorted. So here's the algorithm. It's kind of what you'd expect, which is I will look at the smallest item in the first 2 arrays, or in the only 2 arrays, I guess. And well, where do I know what the smallest item is? It's at the front because they're sorted. So 2 and 4, which one should I copy into the big, gigantic array first? Well, 2, because it's smaller. So I copy the 2 over. OK, great. Now I look at what's the smallest item on the left that I haven't copied yet? Well, it's 3. And I know that because the array is sorted. What's the smallest item on the right that hasn't been copied yet? It's still 4. The 4 hasn't been copied yet. So on the left, I have 3. On the right, I have 4. Which one should I copy next? I'll copy the 3 next. Okay, great. There's the 3. Then I ask again, what's the smallest thing on the left side? Well, it's 6. What's the smallest thing on the right side? It's still 4. It's still waiting to be copied. This time, 4 is less than 6. So we'll copy the 4. Okay, good. What's next? On the left, the 6 has not been copied, still the smallest item that has not been copied. On the right side, 5 is the next thing to be copied. Which one is less? Well, it's 5, so I'll copy the 5. And hopefully you're getting the hang of it. So next, 6 and 7, I'll copy the 6. Okay, good. 10 and 7, I'll copy the 7. Good. 8 and 10, I'll copy the 8. And at this point, I have run out of items to copy on the right array. All the items on the right are done. So all I have to do is go to my left array and copy all the remaining items one by one until I'm done. So that's my merging process. I took 2 sorted arrays and I created one larger array. Thoughts, opinions, questions on merging? Try and guess what the runtime is while I go find the original slides. Okay. Okay. So there's the picture you just saw. So the question for you is, what's the runtime of merge sort with respect to n if that's the length of both of the arrays? So this array and this array, if I add them all up, I get n items. Or in other words, this gigantic merged array has size n. What's the runtime of merge sort with respect to n? Thoughts, guesses? We'll do hands. Theta 1? Any log n takers? N takers? Some? Okay, n squared? Okay, I also think it's n. And the rough idea is, well, I have to look, or I have to copy n items. And every step that I copy an item, I do a comparison, and that takes constant time. So it's a linear time merging algorithm. Okay, so we saw selection sort, we saw this merging operation, and so now here comes the trick that's going to unlock merge sort for us. So first, we remember that if I had an input array of size 64 and I selection sorted it, by the way, SS stands for selection sort on this slide, well, that's going to take roughly 4,096 arbitrary units of time. And this is just me kind of guessing at how long this would take. It's not an exact count, but I can use it to compare against other algorithms if I'm careful. But here's my trick, which is I realized that selection sorting this big array was slow. It's n squared. So what if instead of sorting one big array, which is slow, I sort 2 smaller arrays, which are fast? So I could take this big array and I can split it into 2 smaller arrays, each of size 32. And then I'll selection sort the first half, then I'll selection sort the second half. Okay, that's good. But I'm still not done because now I have 2 smaller arrays which are sorted, but that's not my answer. I want the big final array. So if I have 2 smaller sorted arrays, how do I get the big one? Well, we could just use the merging operation that we just saw. So I selection sort the left half, I selection sort the right half, and then using my new merging operation, I merge the 2 sorted arrays together into one large size 64 sorted array. So how long does this take? If I use a similar analysis from before, I could say, well, the size 32 array, it takes approximately 32 square time to complete, which is 1,024 arbitrary units of time. And same with the right half. The 32 sized array takes 1,024 arbitrary units of time to complete. I have to sort both the left half and the right half. So if I add them up, I get 2,048 arbitrary units of time to do the selection sorting. But I'm not done because I still have to merge the 2 halves together. And I remember that merging is a linear time operation. So if I have 64 items to merge, it will take me approximately 64 arbitrary units of time to merge them. So I can add everything up. There are 2 selection sorts I have to do, plus a merge. And if I add them all up, I get 2,112 arbitrary units of time. And you'll notice that's less than 4,096. So whatever I did, it seems like I did a pretty good job. I took something that used to take around 4,000 units of time, whatever that is, and now using the same metric, it's 2,000 units of time. It's not an exact count, but it at least shows me that my algorithm has gotten faster just by using this little trick where I split the array up. By the way, if the arbitrary units of time thing is making you uncomfy, that's okay. You could also do the analysis using n, and you'd get an expression that looks like this. So the merging would be n time, and then each of these two selection sorts, well, it's size n over 2. The algorithm is n squared, and there's 2 of them. So you can use the math too, but I find it a little bit more intuitive and beautiful to see, look, I went from 4,000 to 2,000. Like I get an emotional reaction from that. Hits me in the gut when I see 4,000 to 2,000. But if you like to, and if this impresses you, you're totally welcome to use the mathematical expression as well. One thing I will say, though, is that asymptotically, the algorithm is still in the theta n squared family. Remember, there are so many different functions in the theta of n squared family. This is one of them. After dropping all the constants, it's still theta n squared, but it's a faster theta n squared. So it's still n squared asymptotically, but maybe the constant's a little bit better, as we saw when we did estimated counts. So that's our first improvement to selection sort, which is split it in half, selection sort each side, merge them back up. And I did some analysis to show it's faster, but it's still n squared. Thoughts, questions? You're not impressed yet? Okay, well, maybe I'll impress you with this next trick, which is we shouldn't be satisfied at this point because we found something that makes merge or selection sort faster, which is to split into 2 halves, then selection sort it back. So what if we just tried the same trick again? So instead of sorting this big 32-sized array using selection sort, what if I also split that 32-sized array into 2 smaller arrays of size 16? And for my other size 32 array, I also split it into 2 smaller arrays of size 16. Well, now I have to selection sort 4 arrays, each of size 16. But that's not my final answer. My final answer shouldn't be 4 separate arrays. It should be 1 big array. So I have to take my 4 smaller arrays and merge them back up into 1 big array. And I think the most natural approach to do this is to do a 2-layer merge. So I take 2 of the size 16 arrays, build a size 32 array, and then I take the other 2 size 16 arrays, build a second size 32 array, and finally I take my 2 size 32 arrays and I merge them back together into 1 size 64 array. So it's kind of like what you'd expect. I pulled the same trick, but on those 2 size 32 arrays, and now I have a 2-layer merge. Okay, so again, we can use some rough numbers to see how much faster this is. And if you don't like it, feel free to use expressions in terms of n. It's the same thing. But let's see. Well, first I have to selection sort 4 of these small arrays. Each one takes 16 squared arbitrary units of time, which is approximately 256. There are 4 small arrays I have to sort. So I have 4 times 256 at this bottom level. And then I have to do a bunch of merging. In particular, I need to merge 2 of these size 16 arrays. I know merging is linear time, so that costs me 32. And then over here, I have to do another merge. That costs me another 32. And then I have to do 1 big merge, and that costs me another 64. So if I add everything up, look, I've gone from 4,096 if I use just selection sort, and now I'm all the way down to 1,152. Even better. If you did this with expressions, it would unfortunately still be n squared. But we can see that in real life, if I ran experiments, this would generally be faster, which is pretty cool. OK. So are you satisfied? Should we go home and say, we're done, we split it into 4, and everything's good? Well, what if we get even more bold and we say, what if I split the 16 into 2 small arrays of size 8, and then I split each of those into arrays of size 4, and then I split again, and I split again? Well, you could keep doing that. And so that's what we could try, which is we keep splitting and splitting and splitting, and we selection sort the smaller arrays. But if you keep splitting and splitting, this is the part that's kind of mind-bending. If I split all the way down to 1, how do you selection sort an array of size 1? Is that fast? Yeah, it's pretty fast. Do you need to selection sort an array of size 1? Like if I gave you an array with 1 item, how do you sort it? Or you just look at it and you're like, done, it's sorted, right? So, well, maybe if I split all the way down to arrays of size 1, there's no need to even use selection sort at all. I split all the way down, and now instead of using selection sort at any point, I actually let all the merges do the sorting for me. So it's kind of mind-bending that I went from making a selection sort a little bit better to going all the way down to the base case, and suddenly there's no more selection sorting to be done. I go all the way down to arrays of size 1, and my base case is, how do you sort an array of size 1? It's done, it's right there. So what if I did that? And so now the question for you is, well, what happens if I use this merging and splitting operation all the way down as far as I can go? Do I still get an n squared algorithm, or has the asymptotic character completely changed? Kind of interesting. So I can do the math. I'm not going to do so on this slide. But if you computed, you would actually get 384 arbitrary units of time if you split all the way down and you didn't selection sort the arrays of size 1. So I actually went from 4,096 all the way down to this. But the question was, if I did it in terms of n, would I still have an n squared function with just a lot of smaller constants? Or would this actually be a totally different asymptotic behavior, which is kind of interesting? So that's what we're going to explore next. But are we feeling OK about this new fancy algorithm where I split all the way down to the bottom and I let the merging do all the work? It's kind of cool. OK. So order of growth. I think you might have seen this when we talked about the asymptotics lecture, or maybe some of the asymptotics assignments. So maybe it looks familiar. But the worst case runtime of merge sort, I could do the same analysis that I've been doing over and over again. But instead of using actual numbers, I will now substitute in n. So let's do it. At the very top level, and here by level I'm talking about splitting the array up over and over. At the very top level, when I had just one big array, well, what work did I have to do at this level? I had to take two small arrays of size n over 2 and merge them into an array of size n. So I did n work at the top level. What about this next level? Well, I have this array of size n over 2. How was that array produced? Who gave me this size n over 2 array, and how much work did they do? Well, whoever produced this n over 2 array had to take two smaller arrays of n over 4, merge them into an array of size n over 2, and that took n over 2 work. And likewise, whoever produced this n over 2 array had to do n over 2 work of merging. So in total, at this layer, I have n over 2 plus n over 2, which is still n. So I still have n layers or n amount of work at this layer. What about this next layer? There are 4 arrays here. Each one is of size n over 4. How long does it take to produce an array of size n over 4 in this particular algorithm? It takes n over 4 time, because all the arrays are produced from a merging operation. So if I have 4 arrays, each one of size n over 4, and each one takes n over 4 time to produce, well, then the total amount of work done here is 4 times n over 4, which turns out to still be n. And if you do it again at the next layer, you have 8 arrays. Each one takes n over 8 time to produce, and you get n again. So it seems like at every level, the amount of work done is n, 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 n. And so if I want to add up the total amount of work done, I just have to figure out how many levels are there. So the first level, the arrays are of size n, and then n over 2, and then n over 4, n over 8. So I can count up how many levels are there. In other words, how many times do I have to divide n by 2 until I hit 1? Well, that's the log n sequence, again, from all that asymptotics that you spend so much time practicing. So overall, the picture is like this. At every layer of work, or at every layer, there's n work done in total. There are n, or log base 2 of n levels, because that's how many times I have to split the array before I get to the base case of size 1 arrays. So my overall runtime is theta n log n. That's kind of cool, because it's no longer theta of n squared. By splitting all the way down, I totally changed and improved the asymptotic behavior of this particular sort. By the way, if you're not comfortable with the fact that, well, what if n was 7? And then when I split in 2, I can't really evenly split in 2. One of the arrays would be size 3, and one of them would be size 4. Well, good for you. You can totally do the analysis even if n is in a power of 2. But the exact count would be a little bit more tedious. But it's still possible, and you would still get n log n. I won't do it here. Hopefully this is good enough to convince you it's n log n. But if you want to, you could be more rigorous and also deal with facts like n could be odd or something like that. OK. Great. So that's merge sort. Now we've seen it. What happens is you take every array, and you split it into two halves. You merge sort the left half, you merge sort the right half, and by merge sort, I mean recursively perform the algorithm that you've already done. And the base case is if you split all the way down to arrays of size 1, then there's nothing to do. So that is how you say merge, or that's how you describe top-down merge sort in a couple of sentences. Here's a reminder of merging, although I won't do it again. And so remember, you split the array into two halves, and you merge sort the left half recursively. So whatever algorithm we're doing right now with all the merges, do it on the left half, then do it again on the right half, and then finally merge everything together. By the way, if you want to know how to implement this in code, you could perhaps have two integers, I and j, to keep track of like the next index of this red array and the next index of this blue array. So if you want to, you could do that, but the idea is kind of the same. 2 and 17, I'll copy the 2. 15 and 17, I'll copy the 15, and you get the idea. OK, copy the 17, copy the 19, 26, 32. And since the left array is out of elements, I just copy everything from the right, and I'm done. That's merge sort. OK, we've now seen 3 sorts. Your chance to ask any questions you have about any of the 3. We saw selection sort. It was our very first one. It was slow because we looked at the elements over and over again. Then we saw heap sort, and we also saw a little trick to do it in place, so you don't have to create a bunch of extra arrays. But heap sort, turns out most people don't use it in real life. I forget if I said this last time. Something you'll see more in 60UNC. But it turns out heap sort, if you try it in practice, it's just not that good. It's a little bit slower than other sorts like merge sort, so no one really uses it, although I find it kind of pretty to use a data structure to sort. And then finally, today we saw merge sort. It's a beautiful recursive algorithm. In practice, if you ran experiments, it's faster than heap sort. And my space complexity is theta of n because I had to create this extra array to finish my merging. Thoughts? Questions? Yeah. That's a good question, which is, could I do merge sort operations in parallel? Justin looked up. Do you have an answer? OK, that's a good answer. I'll repeat it quickly for folks on the recording. But basically, what we said was, is it possible to do merge sort in parallel? And you'll see more parallel code in later classes. But the idea is maybe you give the left half to one computer, and you give the right half to a different computer. They do the work at the same time. They report back to you, and you do the merge. It's possible. And I don't know if you'll get asymptotic speed up, because organizing all the parallel computers can take time too. And it's not something we'll analyze in this class. But it's an interesting thought. Any other interesting thoughts? OK, great. So those are our 3 sorts so far. I have one more to show you, I guess, which is insertion sort. So hopefully you're ready. OK, here's insertion sort. So insertion sort says, well, first, I have no output. Here's my input. And so here's what I'll do. It's one of those things where I don't really know how to say it, but I think once I show it to you, you'll see what I'm trying to get at. So I will first put the 32 in the output array. That one is almost so simple, I can't describe it. Now let's look at the 15. So my choice for you is, would you like the 15 to go to the left of 32 or to the right of 32? Well, I like it to the left because it's less than 32. What about this 2? Do you want it to be to the left of the 15? Do you want it to slot in between the 15 and the 32? Or do you want it to be to the right of 32? Well, I think it should be on the left because it's less than 15 and 32. What about 17? Where should it slot in this output array? I want to slot it right there in between 15 and 32. What about the 19? Where does it slot? It slots right there. So insertion sort looks at every element and somehow slots it into its correct place. So 26, where does it slot? Between the 19 and the 32. 41, it slots at the very end. 17, right there. 17, right there. So that's insertion sort naive version. I take every element, and I slot it into the correct place in my output array. So that's the picture. I don't know how else to describe it besides showing you the picture, but that's naive insertion sort. Now, one problem with naive insertion sort is, how would you actually build this in Java? Because here I'm showing you slotting elements in between arrays, but that's not really something you can do with an array in Java. Maybe if you use the list or something. But I haven't really presented this as a full algorithm. So I'm going to show it to you one more time. It's going to look a little bit different, but it's going to be more realistic to implement than the naive picture I'm showing, although in both cases, the operations I'm doing are the exact same. OK. So let's do it in place. At first, the algorithm might look different. If you go home and think about it, maybe one night when you're sleeping, you'll be like, wait, they're actually the same. And so, but for now, if you want to treat it as something a little bit different, it's OK. So here we go. Not only am I going to make this more realistic to implement, I'm also going to do it in place. So I don't need a new output array where I'm slotting elements left and right. I will do everything in place. So I'll start at the left. I'll go all the way to the right. And I will consider every element. And for every element that I consider, I will say 32, you are now the traveling item. So like pack your bags. You're going on a trip. And you're going to start moving backwards, that is, toward the left, until you find your rightful place. So again, the first example is almost too simple to describe. The 32, it packs its bags. It looks to its left. There's nowhere to go. So its journey is over. It stays there. OK, here comes the 15. So the 15 is now the traveler. So 15, pack your bags. You're going on a trip. And you're going to start moving toward the left until you find your rightful place. So 15 looks to the left and says, should I be to the right of 32? Well, no, because I'm less than 32. So I'm going to travel to the left. And the way that I travel is I'm going to swap elements until I find my rightful place. So 32, 15 should not be to the right of 32. So they will swap places. And you can view it as the 15 traveling toward the left. And now the 15 looks toward the left and says, there's nowhere else for me to go. I must be in the right place. Good. Now we look at the 2. The 2 is ready to take its trip. So it looks to the left and says, I have some swapping to do. So I'll swap to the left of 32. You see, it's moving toward the left. And the way that I move is I swap elements. So the 32 gets swapped. And now the 2 looks to this left and says, am I in the right place? No, because I shouldn't be to the right of 15. So I will swap places with 15 as well. And you can view that as the 2 traveling even further. And finally, it travels, and it looks to its left. There's nowhere else to go. So it's happy where it is. Now we do the 17, and we travel. So it looks to its left. The 32, we need to swap. In other words, the 17 has to start traveling. OK, good. Now the 17 looks to its left and says, should I go further? Well, no, because I'm greater than 15. So I'm happy where I am. This is my right place. I will stay. My trip is over. OK, good. Then we look at the 19. It travels. And in this case, it has to do one swap, and it's happy where it is. OK, good. The 26, it travels once, and it's happy where it is. The 41, it doesn't need to travel at all, because it looks to its left and says, I'm happy where I am. And then this 17, it's going to have to travel some distance. And if you feel like it's a long distance, then you might have a bad feeling about the runtime we're about to do. But this 17 is going to have to travel all the way back. So if you just stare at the blue, you don't look at the numbers and you stare at the blue, look, the 17 is going to travel back. See how it took a trip from over here to over here? OK, good. But the way that you actually implement that traveling is you do swaps. So the 17 and the 41 swap, and then the 17 and the 32 swap, and then the 17 and the 26 swap. So the swapping is how I actually implement the traveling without having to create, for example, a new output array or a fancy data structure like a list. OK, good. And then finally, here's the 17. And I swim it or swap it all the way till it finds its rightful place. OK, that's actually the same algorithm as the one you just saw, where I slotted elements in place. And if you think about it at a deep level, they're basically doing the same thing, which is I'm taking every element and I'm slotting it in its right place. But this version is more realistic for me to implement in code. And it also doesn't require a separate output array. That's why it's in place. OK, that's insertion sort. Satisfied with it? OK, by the way, just because I know a lot of text popped up in the process of this demo, I will say there's an invariant, which is that when you designate, say, 26 to be the traveler, everyone to the left of 26 is already sorted, because all of these elements have already made their journey and found their home. So if everyone has found their rightful home to the left of 26, I know everyone to the left of 26 is already sorted. So that's a nice invariant you can use if you're thinking about insertion sort. So for example, here, when the 2 is about to travel, the 2 knows that everyone to the left is currently sorted because they've all traveled before and found their rightful place. But temporarily, as the 2 is moving, it might temporarily break the invariant, like 15, 2, 32. That's not sorted. But once the 2 finishes its journey, then everything to the left of the current item will be sorted again. So if you like, there's an invariant to make thinking about selection sort helpful. As I consider elements, everyone who's traveled is in the right place. Although they might have to temporarily shuffle around due to traveling, but once they're done traveling, everyone I've considered so far is in their right place. Okay. Go 17, go. Okay, you're there. That's insertion sort. Thoughts before I tell you about the runtime? Okay, so here are some examples in text. If you don't like them, because we have to do alphabetical sorting now, that's okay. It's the same idea. So I have the word potato, and the way that I sort it is I look at the P, it travels backwards. Okay, good. I look at the O, it travels backwards, and now I have to be like, okay, HIJKLMNOP. Okay, good. So O comes before P, so I have to do a swap. And then the T looks to its left and says, I'm to the right of P. That's okay. No swaps have to be made. Let's see, the next A. Well, A is at the very beginning of the alphabet, so it has a long way to go. It has to travel all the way back to the front. Turns out that's 3 swaps. Then this T looks to its left and says, no swapping necessary. This O has to swap a bit forward, and so there's 3 swaps. And so if I sort the word potato, I get au-p-t-t-t. Okay, that's the sort of potato. So this diagram, what I'm showing is, well, every time an element is the traveler, I marked it as purple. And every element that's in black is an element that got swapped in the journey of the purple element. So for example, here, when I took the A and I swapped it all the way to the front, I had to swap A with T, and then with P, and then with O. So 3 swaps in total had to be made. By contrast, here, when I had the letter T, it looked to its left and said, no swapping necessary. So at this step, the amount of work done was constant. There was no swapping done. So in total, if I did a count, I would say that this insertion sort took 7 swaps. Here's a larger example, which I will not say out loud. But if I took the word sort example and sorted the letters, every element gets to be the traveler exactly once. So if you look at the purple elements, S, O, R, T, E, X, A, M, P, L, E, every single letter gets to be the traveler exactly once. And that's what each of these rows represents. And all the elements in black represent how long each element took to take its journey. So for example, the E at the very end, when it was time to consider it, it had to take this long journey and swap all the way back here. By contrast, when I looked at the X at this particular step, it looks to its left and says, well, the T is to my left. I'm in the right place. No swaps have to be made. So every row tells me a particular letter being considered, and all of the letters that are lit up in black represent the distance that that particular letter had to travel to find its rightful place. Or in other words, all the letters that had to be swapped with the purple element. So this one took 36 swaps. It's a larger word. OK, so now we know how to count swaps. So the question for you is, how do we count swaps in terms of n? If I gave you an arbitrary word or a list or an array of size n, and I asked you how long insertion sort takes in the best case and the worst case, well, that's what I want you to think about. So try and think about the best case. And what's the worst case of insertion sort? What's the fewest number of swaps I would have to do if someone gave me a best case super lucky array? And what's the worst number of swaps I'd have to do in terms of n, the length of the input, if someone gives me the worst possible array, where I have to do the most traveling I could possibly ever do? OK, so try to think about it. So if I look at this picture, and I think about what's the fewest number of swaps I could do at every layer? Well, the fewest number of swaps I could do is, what if I did no swaps at the first step, and then no swaps at the next step, and no swaps and no swaps, so every element looks to its left and says, oh, there's nothing for me to do. I would like that. That would be nice. And in that case, at every single step, I would do constant work. Every element looks to its left and says, no swaps. And so in that case, at every step, I do constant work. There are n steps because I have to consider every letter at least once. So for that reason, I think the best case is n, or theta of n. Or sorry, so I can say theta of n in the best case. I could also say big omega of n, which is to say insertion sort is always n or worse. It's up to you. But I think that n is the lower bound asymptotically of insertion sort. And what kind of array would give you n? Well, it's if you always look to your left and the item is already in place. So if you try like a sorted array, well, then nobody will do any traveling. You can try it at home, and that will give you n time. Everyone looks to their left and says, there's no traveling for me to do, so everyone performs 0 swaps. So there's n elements. I have to consider them all. Everyone checks to their left and says, no swapping for me to do, and that's n time. What about the worst case? Well, the worst case is, what if this s had to travel as far as possible, and then the next element had to travel as far as possible, and this element had to travel as far as possible? What's like the maximum distance everyone has to travel? And remember, the distance also tells me how many swaps I have to do. The more swaps I do, the slower the algorithm is. So this s, it's already at the end of the array, so it can do no swaps. Then this letter could do 1 swap. This letter could do 2 swaps. This letter could do 3 swaps. This letter could do 4, all the way until I get to the last letter, which could potentially, in the worst case, have to travel all the way back to the front of the array. That would be n swaps. So my total sum would be 1 plus 2 plus 3 all the way up to n. And that gives me a theta of n squared bound in the worst case. Or you could say big O of n squared to say selection sort is always n squared, or better in all cases. Okay, so that's selection sort. Best case, worst case, thoughts, questions? If my array is lucky, nobody travels, and it's theta of n time. If I'm unlucky, everyone travels their maximum distance, and I get n squared. Also, if you like the pretty geometric arguments, you could also count the number of swaps. You'll see you get the area of a triangle, which is kind of cool. So that's another cool way to get the n squared if you want. Question? The note at the bottom, yes. So it says technically I could say big omega of 1, because omega, and it's a good question by the way, because these symbols always trip people up. So big omega basically says selection or insertion sort. I keep messing that up, sorry. Insertion sort is always running in time linear or worse. That's what big omega means. You can think of it as greater than or equal to. So the runtime is always n or worse. And the way I can say that is I can say big omega of n. And that represents all of the functions that are bigger than n. So it could be n squared, could be n cubed, could be n to the 100, could be 2 to the n, whatever. All of those functions are encapsulated in the family of omega of n. But I could also say omega of 1 because it's still technically true that insertion sort is constant time or worse. If I think about all the possible cases of insertion sort, they are all constant time or worse. That family of functions, which is larger, also includes all of those insertion sort runtimes. So if you think of asymptotic bounds as like a family of functions, well then all the runtimes of insertion sort, they fall into the big omega of n family, and they also fall into the big omega of 1 family. But if you said big omega of 1, it's a little bit of a jerk move because technically big omega of n is a tighter bound. So the way I kind of think about this is if you think back to numbers, and sorry I'm digressing a little bit, but let's say I was thinking about a secret number, and I told you the number I'm thinking of is greater than or equal to 7. Well, if my number was exactly 7, that might be useful to tell you. But if I was thinking of a number like, or if I was thinking like a number like 7, and I said, the number I'm thinking of is at least 7, okay, that's good, it's a tight bound. I could also tell you, the number I'm thinking of is at least negative infinity. Sure, but that doesn't tell you as much information. I'm kind of cheating by telling you that. So if that helps at all, that's another way of thinking of bounds. I want the bound to be as tight as possible to be the most informative. Okay, ask me more about it later, but it's a good question. Anything else you want to know? That was a good digression. Okay. But the important thing on this slide, by the way, is just that insertion sort in the worst case is linear time, and it's quadratic time or n squared time in the worst case. Okay, good. So we have now seen 4 sorts, and I've told you their worst case runtimes right here. Selection sort and insertion sort are n squared time. Heap sort and merge sort are n log n time. So here's an interesting puzzle for you then, which is let's say I have 1,000,000 integers, and I merge sort them. So I read the integers, I merge sort them. After I merge sort the integers, are they sorted? Yes, because I just sorted them. Good. And now, what if I took one number and I changed it? So I have this 1,000,000 length sorted array. And I look through it and I'm like, there's a number 5. I'm going to change it to be -100. Or I'm going to change it to be 20 or something like that. Then I want you to sort the resulting array using any algorithm that you want. Which one do you like best? If I guarantee for you that the array is totally sorted, but I took one element and I replaced it with some other number. So I took a 5 and I replaced it with -100 or something. So it's kind of an interesting puzzle. And maybe you get the answer from the story that I've been telling so far and the section that we're talking about right now, the specific sort. But if I had an array, it was almost sorted in the sense that only one number was in the wrong place, which of these would be fastest? Well, turns out that if my array is almost sorted, insertion sort is actually really fast. So for example, here's the array that I was just talking about, where almost everybody is sorted, and the only person in the wrong place is this letter, which I've swapped out to be B, and all the other letters are in the right place. Well, because everyone's in the right place, if I did insertion sort, every element, A, E, E, L, M, O, everyone would look to their left and say, there's no traveling for me to do. The arrays are already sorted. If I look to my left, everyone to my left is less than myself. I have no sorting that needs to be done or no swapping. So every single letter does a constant amount of work until I get to the incorrect letter that I changed, which is B. That letter has to do a little bit of traveling to find its rightful place. And everyone after that just looks to their left and says, there's no traveling for me to do. So it turns out, if I only have arrays that are almost sorted, so for example, only one of the elements is wrong, or I maybe swap 2 of the elements. If I know somehow that my array is almost sorted, it turns out insertion sort is really good because most of the letters don't have to do any traveling at all, and you just take the one problem and you just fix it by traveling that one letter. Still have to check all the letters, but most of them, the checking will be fast because nobody does any traveling. So it's kind of cool that even though asymptotically insertion sort chokes and gives you this bad runtime, it turns out it's actually, even though it chokes and gives you the bad runtime, turns out that in specific cases like this, insertion sort does pretty well. It's kind of cool. And by contrast, you can try something like heap sort. What would heap sort do on an almost sorted array? The first thing it would do would be turn this into a max heap. So this array is almost sorted. Heap sort would like shuffle all the elements around, put the larger elements at the front and the smaller elements at the back to build your max heap. And then it would delete everything out of the max heap and shuffle everything back in place. So we can see kind of intuitively that if I used heap sort, things would be slower because I have to mess up the whole array and then fix it. Whereas in this case, most of the array stays in place, and I just take the one mistake and I travel it backwards until it finds its right place. So for specific cases, insertion sort might be better. So it turns out for this particular case, I like insertion sort. OK. Here's another case where insertion sort does better. And this one is not as obvious as the example I just showed to you, but I will describe it anyway. It turns out that if arrays are very small, and by small, it's something you have to run experiments to find the exact number for, but it turns out around 15 or so is small for the purposes of this slide. It turns out if I have a very small array, say 10 elements or 7 elements, it turns out if you just run experiments in real life, insertion sort turns out to just be faster than the others. This is one of those things that's hard to prove necessarily because the array is so small. And remember, in asymptotic analysis, I care about n blowing up to infinity. But in this case, I'm specifically concerned about arrays that are small. So the analysis is a little bit different. It requires doing some real-life experiments. But it turns out that insertion sort is actually the fastest sort if your array is very small. And the best picture that I can give to you is that, well, think about how you would merge sort an array of size 7. Well, what would merge sort do? Merge sort does the thing where it's like, the array is size 7. So I'm going to give you half of the array, and I'll give you half of the array. We'll sort each half, and then we'll come back together and organize our results. So merge sort is doing something like dividing and conquering, where it says this array is big. You can take half of it. Then you take half of it. And then afterwards, you finish, and we come back together, and we organize it. And then each of those halves says, OK, you get half, we'll come back and organize our results with a merge. And then on the right subarray, you take half, and you come back and organize your results. So merge sort is doing all this hard thinking of, okay, let's see, here's the subarray, here's the subarray, here's the subarray. It's dividing up the work. But what does insertion sort do? It says, well, forget all that. I'll just swap every element into its right place. So while merge sort is sitting there delegating all the work and saying, okay, you do this half, and you do this half, and then you do this quarter, you do this quarter. Well, by the time merge sort is done doing all the splitting, insertion sort has probably already finished sorting the array. So that's my rough intuitive picture. It's not a proof, but it kind of gets at the idea that merge sort is very concerned with organizing its sort, whereas for a very small array like this, you might as well just get it done using insertion sort. Okay. By the way, kind of cool fact is that if you look inside Java, which has implementations for things like merge sort, it turns out that if you go into Java and you implement or check the implementation of merge sort, which I won't click on, it actually does this, which is if the array is very small, you split and split and split, and the array gets to a small size, it doesn't actually split all the way until the arrays are of size 1. It just splits until the arrays are small enough and then does insertion sort. So it doesn't merge sort all the way to the bottom. It calls it quits once the array is small enough, does insertion sort, turns out to be faster in real life. OK, at this point, you've seen 4 sorts. And there's actually more out there, and we'll see one more probably next time. But there are 4 sorts. And by the way, this is the point, and I think I'll have a slide for this, hopefully. OK, this is the point where you're probably sitting here and you're thinking, I feel like I have just seen the same algorithm 4 times. And the reason why you're thinking that is you have basically seen the same algorithm 4 times. So this is the point where it's very easy to get lost in all the sorts and the operations and say, what's the real difference between selection sort and insertion sort? Or what's the difference between heap sort and merge sort? They're both n log n runtime. So to me, the way to separate out the sorts, because it's very tricky to confuse them and feel like you just saw the same thing over and over again, is I try to think about what's the operation that makes the sort work. So for example, in selection sort, what was the operation I was doing over and over and over again to make the sort work? It was find the smallest item. So the key operation that made selection sort work, and also heap sort by extension, is you find the smallest item over and over and over again. So I could maybe even call it something like find the smallest item sort. That's not what they call it, but that's the key idea that makes selection sort work. By contrast, insertion sort, which might have felt really similar, it uses another core operation that's different. It does not find the smallest element. You go back and look at insertion sort, we never bothered finding the smallest element. Instead, we figured out where to put the current item. So the key idea that makes insertion sort work, the operation you do over and over again, is that traveling operation where you find out where the item needs to go. And what about merge sort? It didn't do either of these ideas. The core idea that made merge sort work, the operation you do over and over and over again, is I have 2 sorted arrays. How do I combine them into one larger sorted array? So every flavor of sort that you've seen so far is backed by a specific core idea. And if you're ever feeling like, I feel like I've seen the same sort 5 times at this point, these are the ideas that I think of to tease them apart. So I'll give you a quick sort preview. I was going to say a quick sort preview, which also works. And then we'll come back next time and talk about it. So it turns out quick sort also has an idea, but the idea is going to take me one whole lecture to explain, which I will do next time. And basically, it also has this extremely weird backstory, which I'll like briefly mention, which is that the person who invented quicksort is Tony Hoare. He was trying to work on this like machine translation algorithm, and this is 1960, so the algorithm wasn't sophisticated at all. Here are some details. But basically, somewhere in his algorithm, because it's 1960 and hardware was really bad, he had to sort a sentence. And this is 1960. There's no Google. There's no ChatGPT to ask, how do you sort something? So he had to come up with the sort himself. And what you're about to see next time, which will take me basically 1 hour to explain, will be Tony Hoare's first idea from 1960. So how a novice programmer came up with something that you and I will take an hour to explain is beyond me, but that's going to happen next time. Do you have any final thoughts or questions before I leave you on this quicksort cliffhanger? Did I actually finish early today? I finished like 10 seconds early. OK, go enjoy your extra 10 seconds of freedom. I'll see you next time.